Good morning. We are here to conduct a technical deep dive into the Claude Skills architecture and deployment documentation.
I have the source material loaded, and I am ready to dissect the architectural mechanics we have in front of us today.
Excellent. The objective of this session is to analyze the framework provided for automating repetitive development tasks. For those of you listening and evaluating your own tech stacks, we are looking specifically at the transition from manual context setting, what you would typically call prompt engineering, to a highly structured, markdown-based instruction set.
Understood. We need to focus on how this architecture shifts the operational paradigm from ephemeral, session-based interactions to persistent capabilities. I'm prepared to break down the specific data points regarding context optimization and the various deployment scopes defined in the text.
Let's begin the sequential analysis. Slide 1, Claude Skills architecture and deployment.
Pulling up the data for the first section now.
The strategic intent presented here is to define a new standard for automating development workflows. The documentation positions this not merely as a minor feature update, but as an executive guide to a fundamental architectural shift. The primary definition of the framework revolves around using standard Markdown files, specifically .md files, to teach the system specific capabilities just once for automatic application later.
Precisely. Looking at the specific mechanisms listed on the slide, there are three critical data points to evaluate. First is the core benefit, which the text explicitly defines as the elimination of repetitive descriptions.
Which addresses a massive friction point. You are constantly re-explaining feedback structure or formatting rules to the AI.
Exactly. The second data point is the mechanism itself. The document identifies these as agent skills. The text specifies these as folders of instructions and scripts that the agent discovers to execute tasks with high accuracy. The key term there is discovers it is a retrieval model. Finally, the third point is the visual output flow,
which clearly shows the transition from the AI processor directly into a .md output file.
Yes, confirming that human-readable Markdown is the fundamental unit of storage and execution for this entire framework. It is human-readable code acting as machine-executable logic.
Moving on to the root cause of the issue. Slide 2, the friction of repetition.
The premise here provides a very stark look at workflow latency.
It does. The strategic intent of this slide is to diagnose the operational inefficiency that necessitates this new architecture in the first place. The text argues that manual context setting leads directly to workflow inefficiencies and consistency errors in development cycles. If you have to constantly restate task parameters, you inherently introduce human error.
And the graphic provides a detailed breakdown of these pain points. It illustrates what we can call a cycle of inefficiency. It starts with the developer issuing a command to fix this code.
Which immediately spirals because the AI lacks the specific environmental constraints.
Right, it spirals into wasted compute. The AI generates a generic, unusable response. That triggers a context-missing error state, which forces the developer to manually input a correction, like use PR format A.
It creates a reactive loop where you
are correcting the tool instead of utilizing it, exactly. The slide quantifies the cost of this loop as wasted mental energy and time spent reminding the AI of basic preferences. But the most critical signal identified here is a specific rule quoted directly in the text.
If you explain context twice, it is a missing skill.
That is the exact metric. It creates a binary rule for developers. It changes the threshold for automation from high-frequency tasks to literally any repetition whatsoever.
Let's examine the proposed remediation for this cycle. Slide 3, the Skill.md solution.
This section details the exact technical components required for deployment.
The core intent here is to establish skills as persistent, auto-executable knowledge bases. The solution relies entirely on standard Markdown to function as a persistent repository of instructions. It represents the complete transition from a transient prompt that disappears after a chat to a stored asset that lives in your directory.
Unpacking that technical structure, the slide breaks down two mandatory Markdown headers required for the parser to function. First is the description header,
denoted by standard Markdown syntax, the two hash symbols.
Yes. The example given in the text is check PRs for style guide compliance. This description is not a comment. It acts as the semantic matching vector for the system. The second required header is instruction, which contains the actual execution steps, such as ensure camel case or verify imports.
So the architecture logically separates the trigger from the operational payload.
Precisely. The paradigm shown is a linear workflow of teach, once leading directly to automatic execution. The three pillars identified in the data are format, which is standard Markdown, function, which is persistent knowledge, and components, being the instruction body plus the description. You're essentially writing natural language software to govern the AI's behavior.
That logically leads to how the system queries these components in real time. Slide 4, activation logic, how Claude decides.
This is the core decision-making engine of the framework.
The strategic intent here is to explain how Claude utilizes a semantic matching process. The goal is to load skills strictly on demand, ensuring that the system only activates specific instructions when the task explicitly requires them. This prevents the AI from being overwhelmed by irrelevant rules.
The data details a step-by-step logic flow for this activation process. It begins with a trigger, which is initiated by user intent. The example provided is the simple request, review this PR.
Which immediately initiates a system-level scan behind the scenes.
Correct. The next phase is matching. The system compares the semantic meaning of that user intent against all the available Markdown descriptions we noted in the previous slide.
And it is vital to note this is semantic comparison, relying on vector embeddings, not just basic string matching.
Yes, that distinction is critical for accuracy. The final phase is activation, which splits into a binary outcome. If a match-found state occurs, the specific review skill is activated. If it results in no match, the skill remains dormant. This dynamic loading ensures that relevant instructions are injected dynamically without user intervention.
Which is a perfect segue into resource management and token economics. Slide 5, context window optimization.
This directly addresses the fundamental token limits of any large language model architecture.
The intent here is to summarize the efficiency strategy. Skills optimize token usage by remaining dormant rather than polluting the global context window with irrelevant instructions. We are contrasting an inefficient legacy state with this highly optimized architectural state.
Breaking down the contrast presented in the data, the global context approach is depicted on the left and explicitly labeled inefficient. It illustrates a state where all global rules, style guides, and documentation are always loaded,
Resulting directly in token waste.
Exactly. The window is filled with dormant rules, leaving less computational space and attention mechanism focus for the actual code you are trying to process. On the right, the skill architecture is labeled optimized. It explicitly states that it loads on demand.
The selectivity metrics are the key data points there.
Right. The text notes that only the name and description are held in memory initially. That is an incredibly lightweight footprint. The specific operational example cited is that review checklists stay dormant during debugging. This ensures the context window remains entirely clean for the actual code analysis, maximizing the signal-to-noise ratio.
Now we need to evaluate the physical deployment vectors. Slide 6, Scope 1, personal skills.
This defines the first level of the deployment hierarchy, focused on the individual.
The strategic intent here is to define a scope that follows the individual user across all environments. It is designed to enforce individual workflow preferences, regardless of the specific repository or project you happen to be working in.
The implementation details provided specify the exact directory path for this scope. Personal skills reside in the user's home directory, specifically at ~.claude/skills.
Establishing a clear layer of cross-project portability, similar to a traditional .file configuration.
Yes, the diagram illustrates this portability by showing a single developer at the center, with their skills persisting across Project A, Project B, and Project C. The specific use cases listed for this scope include personal commit styles, documentation formats, and code explanation preferences.
So if a senior architect always requires code explained with a focus on latency and security, that preference follows them globally.
Exactly. It operates entirely at the user level, ensuring the AI interacts with them consistently without manual prompting every session.
Conversely, we have the team governance layer. Slide 7, Scope 2 project skills.
This scope overrides those personal preferences to enforce strict standardization.
The intent here is to define repository-specific skills. This ensures team alignment and absolute consistency for anyone who clones the codebase. It shifts the operational control from the individual developer to the project architecture itself.
The technical implementation places these skills directly at the root of the repository, inside a .claude/skills directory. The critical distribution mechanism noted in the data is that these skills are auto-acquired via git clone.
Meaning there is zero manual configuration required for a new developer onboarding onto the project.
Correct. As soon as the code is cloned, the project rules deploy automatically to their machine. The targeted use cases for this scope are strictly governance-focused team standards, brand guidelines, and shared design systems. It programmatically enforces the definition of done for the entire team.
Let's contextualize this capability within the broader ecosystem of automation tools. Slide 8, feature comparison skills versus others.
This matrix is vital for understanding when to leverage which specific tool.
The strategic intent of this comparison is to demonstrate that skills occupy a very unique niche for task-specific automation. We are evaluating them against global prompts and manual commands to understand their relative operational value and efficiency.
Conducting a line-by-line analysis of the matrix, the first comparison is against claude.md files. These are characterized as always on and representing a heavy load on the context window. They enforce global rules.
Like a strict mode that applies to every single interaction regardless of the immediate context.
Yes, it is a sledgehammer approach. The second comparison is against slash commands. These are defined as manual type and task-specific. They are characterized as ad hoc actions.
Meaning they rely entirely on the human user remembering to type the command, introducing the potential for human error.
Exactly. Finally, the matrix highlights the superior operational attributes of skills. They are auto-trigger, meaning no manual typing is required. They are efficient and on-demand, solving the heavy load issue of the global files. And they deliver specialized knowledge right when it is needed. They offer the intelligence of a global rule with the precision of a slash command.
That leads us directly to the practical applications. Slide 9, high-value use cases.
This identifies the areas with the highest measurable return on implementation effort.
The intent here is to highlight the best strategic scenarios to deploy these skills for maximum operational impact. It translates the theoretical architecture into concrete business value for your development teams.
The data details 3 specific operational domains. First is code review. The specific application here is standardizing feedback structures for pull requests.
Ensuring every single review automatically checks for the same security flaws, performance bottlenecks, and structural formatting without human prompting.
Right. It creates an objective baseline. The second domain is brand integrity. The use case is enforcing color palettes, fonts, and design systems automatically during front-end development.
Catching design drift and correcting hex codes before the developer even commits the code.
Exactly. And the third domain is process compliance. This focuses on automating commit message formats, specifically for CI/CD pipelines. It ensures that automated build systems do not fail simply due to a malformed commit message from a developer.
We have analyzed the architecture, the activation logic, and the core use cases. Now we look at the transition. Let's turn to the execution plan.
Slide 10, Next Steps Implementation. This final phase outlines the transition plan to automated skills by auditing current workflow friction points.
The methodology provided in the documentation is highly structured.
It outlines a specific 4-step process. Step 1, audit. Identify repeated instructions.
That audit phase is critical for locating your actual token waste and identifying the repetitive commands your team types every single day.
Step 2, draft. Write Markdown with clear descriptions.
Because, as we established, those descriptions act as the semantic triggers for the activation logic.
Step 3, deploy. Place in the .claude directory or repository root.
Depending entirely on whether you need individual user portability or strict project governance.
Step 4, execute. Auto-run on the next prompt. Start automating workflows today.
That concludes the formal roadmap and our analysis of the documentation. The implementation plan is logical and directly addresses the friction points we identified in the early slides.
I agree. The architectural review is complete. The data supporting the transition from ephemeral manual prompting to persistent Markdown-based skills is thoroughly documented and compelling.
For those of you listening and evaluating your own operations, consider this final thought. If your team's collective intelligence, coding standards, and operational guidelines only exist in a static wiki that nobody reads, are you truly utilizing your AI capabilities, or are you just treating the system like a very fast junior developer who requires constant manual supervision? Thank you for joining us on this deep dive.